All right, hello and welcome back to your Chem 4 lecture. Today we are finishing up chapter 12, pardon me, talking about aldehydes and ketones today, and some of the chemical properties of the reactions or the types of organic compounds that we've been talking about. So starting off with, we'll just kind of point out here the simplest ketone that you probably are familiar with is known as acetone. And this is commonly used as a nail polish remover. Really good solvent for a lot of nonpolar compounds. And so it's really useful. And again, it can be used for nail polish or for other cleaning, for example, in when you're cleaning stuff off the floor, for example, if you're trying to remove a varnish, oftentimes acetone is used. Okay, so but let's go ahead and start by looking at one particular group of molecules, what we're going to call a functional group, that is going to show up again and again during this during these chapters on organic chemistry and then in biochemistry as well. It's what we call a carbonyl group. And what a carbonyl group is it's just a carbon-oxygen bond, and specifically it's a double bond. Now, if you look at your periodic table, you'll see oxygen is much more electronegative than carbon. So you'd predict that if they bond, then they're going to form a polar bond. And sure enough, that's exactly what happens here. So your carbon double bonds to another oxygen, and you get a polar bond out of it. So the two lone pairs on the oxygen plus the electronegativity of the oxygen pulling the covalent electrons to its side result in a dipole with a partial negative charge on oxygen and a partial positive charge on the carbon. Now, there's two of these compounds that we'll talk about here that kind of split at this moment. So the carbonyl group is always the C double bond O. However, the carbonyl group is like a part of other functional groups. So basically, it's a part of both the aldehyde functional group and the ketone functional group. So for the aldehyde functional group, the carbon that's bonded to the oxygen is attached to at least one hydrogen. For the ketone group, however, there are no hydrogen atoms attached to that carbon, and it is attached to two other carbon atoms. That's what differentiates between a ketone and an aldehyde. And as we'll learn in the future, we've got carboxylic acids, we have esters. These functional groups also include a carbonyl group, but they're bonded to other things. So don't worry about those yet. Basically, what we're showing now is ketone is when carbon is bonded to two other carbon groups, and aldehyde is when it's bonded to at least one hydrogen atom. Okay, now the way that we actually draw the aldehyde group, if we're drawing the, if we're using the condensed structural formula, that's the CH3, CH2, CH2, CH3 type, the way that we draw an aldehyde is it's always going to be on the end of a molecule, and we'll put it as CHO. Now, we know that this carbon has to be double bonded to this oxygen when we draw it this way because, first off, we know carbon has to have 4 bonds. Presumably here, the carbon's bonded to another carbon back here. So that's 1. Then it's bonded to this hydrogen, that's 2. But then the only thing left is the oxygen. So the only way you can account for that is if you have a double bond to that oxygen, and that gives carbon its 4 bonds. Likewise with oxygen, it has to have 2 bonds. So in the way we've written this, this oxygen is not bonded to this hydrogen. If it were, we would put OH here. And that's not the case, it's HO. This H is bonded to this carbon, this oxygen is bonded to this carbon. And again, it has to be a double bond. The ketone is just written as CO, basically, in the condensed structural formula. Now, the way this actually looks is, if you're drawing the condensed structural formula, again, it would look like this for the aldehyde, CH3, CH2, CHO. Now, when you draw the line angle formula, which is kind of what I'm going to push you to do more often than not, you're actually going to draw out the hydrogen here that's bonded to this carbon, just as a way of pointing out, essentially, this hydrogen is more reactive than the other hydrogens. So it just comes up more often that you'll need to draw that hydrogen in. For a ketone, if you want to draw the condensed structural formula, it's CH3, and then for this C double bond O, you just put it as CO in line. So the acetone becomes CH3, CO, CH3. And we know that for the line angle formula, it's a double bond from the central carbon to this oxygen, just like what we draw here. So hopefully we're pretty good at that after our work on Lewis structures. But of course, as always, we're learning. And so if you have any questions, make sure to ask in the comments down below. Okay, next up, aldehydes. So we're going to start by naming aldehydes. And the reason that we start with aldehydes is because it's pretty simple, other than the first 4 aldehydes. So the first 4 aldehydes have a common name, and those common names are used almost exclusively. So it's kind of annoying, but we have to teach you sort of 2 separate ways to name the first 4 aldehydes. And then beyond that, we have IUPAC nomenclature. Now, IUPAC nomenclature is really easy here because aldehydes, since they're always bonded to a hydrogen, they have to be terminal. They're at one or other end of the carbon chain. So all you have to do is take the E from the alkane ending and change it to AF. So for example, let's go with pentane. If you had a 5-carbon aldehyde, you take pentane minus E plus al becomes pentanal. Okay. Now let's bring up these common names here for the first 4. A 1-carbon aldehyde is formaldehyde. This is, of course, like a very important molecule that you probably heard used before. Hopefully you don't have to deal with it too much in like a health setting. This is more of a death type of compound here because it is very poisonous, but it's good for fixing tissues. So formaldehyde is basically this compound here. Got a hydrogen on either side. And yeah, it's a single carbon bonded to 2 hydrogens with a double bond to an oxygen. Okay, now if you have 2 carbons, that looks like this. So now it's a CH3COH. Now that becomes acetaldehyde. Okay, 3 carbons then becomes propion aldehyde, and then finally 4 carbons is butyraldehyde. Again, I wish I could tell you that we use the systematic names for these, but that's just not the case. Methanal technically is the IUPAC name for formaldehyde, but in common usage, formaldehyde is still the way that it's used. Okay, so now let's look at some other ones here. So yeah, methanal, ethanal, propanal, butanal, those are the correct IUPAC names for them, but the common names would be formaldehyde, acetaldehyde, propionaldehyde, and butyraldehyde. Okay, so let's go ahead and work on one of them here. I give the IUPAC name for this aldehyde. So again, we're not worried about the common name, we're worried about the IUPAC name. So let's go ahead and give it a shot. So just like all the other compounds that we've named so far, the first step is going to be identifying the longest carbon chain. And of course, just like with the alkenes and the alkynes that we have to include the aldehyde group here. So we're going to be starting from this carbon here that has the aldehyde group on it. So this carbon 1, 2. Now if we go here, that's 3, but obviously that's a dead end. So it's going to be better to go 3, 4, 5. Okay. Now, the first part of this name is just, we've already got it, right? It is simply going to be pentanal. And we don't need to number it 1 because the aldehyde group has to be at carbon 1. So we don't need to give a number for the aldehyde group. However, we should notice there's a substituent now on carbon 1, 2. We have a methyl group on carbon 2. So this should become 2-methyl pentanal. And apologies here. There we go. Should look like that. 2-methyl pentanal. Okay. Okay. Now for ketones, we have a couple different ways of naming them. The way that we do it is in the IUPAC system, the E at the end of the alkane is replaced with -one. And then there's a few that have common names that we're going to worry about here. The way that we do it is sort of like how we named ethers in the previous chapter, or I guess that was in the previous lecture. For example, propanone, which is known as acetone, actually. So that has a double common name here. It has a methyl group on either side of the ketone carbon. So we call it dimethyl ketone, would be the common name. However, we actually have to number where the ketone is usually. For propanone, of course, it can only be in the central carbon. Butanone can only be on the second carbon because, as you can see, if we moved it 1 carbon over, it would just be the second carbon the other way. But for pentanone, for example, you could have a 2-pentanone or a 3-pentanone here. Another point here is you can have a ketone on a ring. So for example, this is cyclohexanone, which is cyclohexane with a ketone group on it. And then of course, in that case, you're going to number from the ketone that's on the ring as number one. Okay, let's go ahead and give it a shot. Now, I'm not going to require you to know any of the common names for ketones because I think that's a little too much to ask, but you should know acetone. That's kind of the most important one here, and acetone is propanone is the way you can think about it. Okay, so let's go ahead and give it a shot now with this one. So with this ketone, again, we want to identify the longest carbon chain that contains the ketone group. So it's going to be closer to this side, right? So we're going to start over here. That's 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon. So it would be pentane again, right? But now we know it's going to be pentanone. Okay, and then let's go ahead and number the carbons. Well, we want to number it from the side that's closer to the ketone. So that's going to be 1, the ketone's on carbon 2, 3, 4, 5, just like that. So we see that the ketone is on carbon 2. So the correct one here is going to be, I can just get this. We go 2 pentanone. How are we done? Not quite, right? Because we also have a methyl group on carbon 4. So we just have to put in 4 methyl 2 pentanone. Oops. And put that in position, 4 methyl 2 pentanone. So that's how you can name these ketones. Again, it's just variations on what we've already learned. But of course, it's always good to kind of review it as you're going along. Okay, now, what is important about this aldehyde and ketone group in this, using the carbonyl group is that the presence of this carbon-oxygen double bond makes aldehydes and ketones more polar. Because you have this partially negatively charged oxygen that has 2 lone pairs that can participate in hydrogen bonds. It can accept hydrogen bonds is the way you can think about it from up to 2 water molecules for both aldehydes and carbons. For both of them, they're very soluble when they have 4 or fewer carbons. But if they have 5 or more, that tends to diminish the solubility. So they're not very soluble up to insoluble. So what we're going to use as the demarcation line is 4 carbon aldehydes and ketones are soluble, and then 5 carbons and up are insoluble. That's what we're going to use as our examples here. Now you see here in your book, it says pentanal and 2 pentanone, for example, are slightly soluble. We're just going to consider them insoluble for the purpose of this class. Basically, it just means that, some of the pentanal and some of the pentanone will mix in, but not a lot. So that's where we'll kind of mark the line here between soluble and insoluble. Okay, so now let's talk about some of the important aldehydes and ketones. We already mentioned acetone. Acetone, if you've ever gotten the acetone nail polish remover, I know there's a acetone and acetone-free nail polish remover, but you probably will recognize the smell. And not just nail polish remover, but also a lot of different glues will use acetone as a solvent so that it dries off very quickly. So again, you'll probably recognize the smell, even if you don't recognize the name acetone necessarily. Next up, we have formaldehyde. Again, you probably recognize that name as well. You probably know it as a fixing agent. In other words, if you have dead tissues, you can store them in formaldehyde, and it basically prevents decay. What it does is all this formaldehyde will cap any of the reactive molecules that would otherwise be subject to decay by living organisms like bacteria or anything like that, and prevent those molecules from breaking down. Now, formaldehyde itself is pretty dangerous. Like, it is definitely a carcinogen. So most fixative agents, like if you're doing a dissection in another class, you probably won't be using formaldehyde itself, but a closely related compound. But of course, like if you watch the old horror movies like Dracula and stuff like that, the specimens that you see in the jars are preserved in formaldehyde. Okay. Oh yeah, I almost forgot this, but ketones and aldehydes can also be responsible for flavors and smells. For example, benzaldehyde, which is a benzene ring with an aldehyde on top of it. This is responsible for the flavor and the smell of almonds. Vanillin is related. It's as you can see, it's a benzaldehyde plus hydroxyl group plus an ether group, and that's responsible for the vanilla flavor. And then finally, cinnamaldehyde here is a ketone, and it's a ketone that is responsible for the flavor of cinnamon. So aldehydes and ketones can show up in flavors as well. Okay, so starting off easy with sample exercise 5. Classify A through D as either an aldehyde or ketone. We're going to pause the video here, let you work on it. So you go ahead, pause, and when we come back, we will take a look at the answer. So pause. All right, hopefully this wasn't too tricky, but here, what you want to do is look at the carbonyl and ask, what is it bonded to? This carbonyl is bonded to 2 other carbons, so that's a ketone. For B, this carbon's bonded to a carbon and a hydrogen. If it's bonded to at least 1 hydrogen, that means it's an aldehyde. Okay, for C, you can see again, the carbonyl carbon is bonded to a carbon and a hydrogen. So it's bonded to a hydrogen, it's an aldehyde. And then finally, we have a ketone here because this carbon's bonded to 2 other carbons. There's no other, can't have a hydrogen in the ring, right? So it's got to be a carbon. All right, okay. And here's a better one. Let's go ahead and give the IUPAC name for each of the following ketones. So go ahead and pause the video here, come up with the name, and then when you come back, we will take a look at the answers. So go ahead, pause. Okay, let's go ahead and go through the answers. So I'll go through it first, and then we'll go through the books. So the way I would look at this is I see I have a ketone here. So I want to start my numbering from over here. 1, 2, 3, 4, 5, 6 carbons. So it's going to be hexanone. And then the ketone is on carbon 2. So it would be 2-hexanone. And there's no substituent, so we don't have to worry about that. Okay, for B, now we've got 1, 2, 3, 4 carbons. The ketone is on carbon 2, so it'd be 2-butanone. But this time we have a chlorine group on now carbon 4. So this should be 4-chloro-2-butanone. Okay, so starting out, hexanone, 2-hexanone, 2-butanone, and then 4-chloro-2-butanone. So that's all you have to do for these names. Hopefully this nomenclature is once you get the hang of it and you do more of the practice problems in the book and on your mastering chemistry homework, you'll get kind of better at it as you go along. Okay, let's go ahead and talk about a few reactions that these alcohols, thiols, aldehydes, and ketones go through. So including the types of compounds from the last chapters or the last lecture as well. So, okay, so one thing that we're going to have is combustion. Yeah, we'll take a look at this. Okay, let's go. Okay, we'll mention combustion here very briefly, but basically, remember, combustion was when we took a hydrocarbon, reacted with oxygen, and produced carbon dioxide and water. Well, now we can do the same thing, but this time with an alcohol, for example. Like this is a flambe dessert, for example. Looks like a pineapple. Yes, or is that shrimp? Well, I can't really tell, but I hope it's pineapple. Anyways, you pour a little bit of alcohol in there, and if it's high enough concentration, it's flammable, so it boom, catches on fire. And the reason that you do that is for something that we'll talk about in the next chapter, where the sugars will actually caramelize a little bit and get a little extra flavor from it. Okay, but first off, let's go ahead and go through this systematically, starting with alcohols, which we talked about in the previous lecture. Alcohols can undergo dehydration when you apply an acid catalyst. So the way we write acid catalyst is just proton, H+. You could also use the hydronium ion, H3O+, if you want to, and heat. Now, what happens when you heat it is the OH group leaves with a hydrogen from a neighboring carbon atom. And this leaves as water. So this here, let me try to circle it here. These two groups leave as a water molecule. And what you're actually left with on the other end is an alkene. So the carbons that did have the oxygen, the hydroxyl group and the hydrogen, now form a double bond. So here we go from ethanol to ethene. And again, this dehydration reaction occurs when you have an acid catalyst and you apply heat. Oops, sorry. Okay, so that's the kind of simplest reaction that we have here for these types of compounds. go. Okay. So now, what we want to say next is we want to talk about the oxidation and reduction of organic compounds. Now, we talked a lot about oxidation and reduction in a previous chapter where we were looking at the transfer of electrons from metals to nonmetals. Now, in organic chemistry, we have kind of a simpler way of looking at it, where basically what we're going to do is we're going to look at the reactants and the products. And a carbon becomes oxidized if the number of carbon-oxygen bonds that it has increase. So if you either add oxygen atoms or go from a single bond to a double bond, you're going to have a oxidation of that carbon that added additional oxygen bonds. You can also track it by what loses hydrogens. So if you lose a hydrogen atom in particular, that's also an indication of oxidation. And reduction is the opposite. Again, if you went from a carbon double bonded to an oxygen to a carbon single bonded to an oxygen, that's a loss of carbon-oxygen bonds. And so you would say that that carbon was reduced. Okay, let's go ahead and take a look here. Now, we're going to start by talking about these different alcohols. Remember, we have primary alcohols. Primary alcohols are where the hydroxyl group is bonded to a carbon that's bonded to one other carbon. When you oxidize a primary alcohol, you take your carbon-oxygen single bond here, you remove a hydrogen from both the oxygen and from the carbon, and you get a carbon-oxygen double bond. Okay, so here, as we can see, we had a single carbon-oxygen bond here, and now we have a double carbon-oxygen bond. The number of carbon-oxygen bonds increased, so this is an oxidation of this carbon. And as you can see, we produced an aldehyde. Now, if you were to further oxidize this aldehyde, aldehydes can be oxidized further to a compound that we'll call a carboxylic acid. Now, we have a full chapter on carboxylic acids, not next chapter, but the one after. So we'll talk about them a lot. There's a lot of properties that are really important for it. But for now, we just need to recognize the name. And here we go from 2 carbon-oxygen bonds to 3 carbon-oxygen bonds. We have a double bond here and a single bond here. So clearly we oxidized again into this carboxylic acid. Okay, now that's for primary alcohols. For secondary alcohols, what happens is you can oxidize it once from an alcohol to a ketone. So now we have this carbon's bonded to 1 hydrogen and 2 carbons and an oxygen. So that's 1 bond oxygen. When it gets oxidized, this carbon and this oxygen both lose a hydrogen. So that leaves you with a C double bond O, a carbonyl group. In this case, a ketone, and that has 2 bonds to oxygen. Since you increase the number of bonds to oxygen, you've oxidized this carbon. Now, here's the thing. This ketone can't be oxidized further because this carbon doesn't have any other hydrogen groups to give up. So if you oxidize a secondary alcohol, it stops at ketone. So just to be clear, oxidizing a primary alcohol, you first go to an aldehyde, then you go to a carboxylic acid. For a secondary alcohol, again, that's where the carbon that's bonded to the hydroxyl group is bonded to 2 other carbons. You can oxidize to a ketone, but you don't oxidize any further. Okay, now what about a tertiary alcohol? Well, in a tertiary alcohol, that's where the hydroxyl group is bonded to a carbon that's bonded to 3 other carbons. Here, this carbon doesn't have any hydrogens that it can give up, so it can't be oxidized. So tertiary alcohols are not oxidized. Okay, now let's go ahead and take a look at how this works in your body. And this brings up one important note here, which is that methanol is a poison. So, okay, people like to talk about alcohol as a poison, ethanol as a poison. And, you know, sure enough, it is. If you drink enough of it, it's really bad for you. But if you want to talk about a real poison, talk about ethanol's cousin, which is methanol. Now, methanol in our bodies, you know, you might not even really be able to see the difference between it and ethanol. It boils at like 60 degrees Celsius, whereas ethanol boils at 80 degrees Celsius. But they look kind of the same. Oftentimes, you'll have it in windshield washer fluid, paint strippers. It's useful as a solvent for those. However, when it's in our bodies, it's oxidized to formaldehyde and to formic acid. And both of these are poisonous. In fact, we talked about formaldehyde as like a fixative. And sure enough, if you put it in your body, it's going to do the exact same thing. For formic acid, that is also a poison. This is the poison that ants use, actually. Formic acid here. Did I want to say anything else here? Oh, yeah. So this is, who knows, hopefully this won't matter to you ever, but if you ever are in the position where you need to ferment your own alcohol, by, you take whatever, humans have done this for forever. Like if you're taking grains and fermenting them and then trying to distill off the ethanol for drinking purposes, whenever you do that, you have to use one of two things. Number one is if you have a copper still. Copper stills help out a lot because they absorb and get rid of the methanol that's produced in the fermentation process. So copper stills are big, but copper is very expensive and it's hard to find. So in the situation where you're doing this on your own, you probably don't have a copper still. Then step two is whatever you boil off from the first fraction, just throw it out the window. So, you ferment the stuff, you get something that's like 10% ethanol by volume. You boil it and you collect the vapors and recondense them. You're going to try to use that to drink, basically. The first fraction of what comes off, just throw it away, because that is likely methanol, and that is likely to very seriously damage your health and your eyes. The rest of it, however, after that, you can use as needed, after the downfall of society. So, okay, so moving on, ethanol. So ethanol is alcohol. This is the compound that acts as a depressant. It kills or disables more people than any other drug. I guess I didn't realize that, but it is an extremely commonly used drug, right? And for example, it impairs your judgment. So if you were trying to drive a car, that can be a problem. If you are a social drinker, so you drink a little bit at a time, you can metabolize about 12 to 15 milligrams per deciliter. And I believe this is in your blood here. I should have pointed that out, per hour. And if you're an alcoholic that has a lot of these enzymes, you can metabolize at a rate of 30 milligrams per deciliter per hour. And that goes from ethanol to acetaldehyde to then you can turn it into carbon dioxide and water. Okay, next up, let's talk about thiols. Now, thiols, we don't really have to talk too much about them, but thiols can undergo oxidation to form a disulfide. And this is only really important in terms of proteins. So proteins are made up of amino acids, and we have a whole chapter on these later on. We don't need to learn too much about it yet. But these amino acids include, for example, cysteine. Cysteine is a thiol, and these thiol groups can be linked together by these disulfide linkages. So a cysteine would be a thiol. It can be oxidized into a disulfide bond, and that can be a way that you can bridge proteins together. Disulfide bonds are really common in hair proteins, for example, and that's why when you burn hair, it smells bad. You have a lot of sulfur in there, and you're smelling the sulfur residues as it burns. But this is what a disulfide bond looks like. It basically, rather than having each of these sulfurs bonded to a hydrogen, now they're bonded together. Okay, I'm not going to make you memorize any of this, but obviously the more you drink, the worse off you are. Okay. Oh, right. And then the chemical tests. So I think this comes up on your homework, but I'm not going to include this in your exam for this section here. So for Tollins's test, you have Tollins reagent, which contains silver. Now, silver ion will oxidize aldehydes, but it will not oxidize ketones. What happens is you take the silver ion, it gets reduced to silver, and in your test tube, it looks like a mirror. So it's a pretty cool reaction, and it can be useful, again, if you're trying to find out if you have a aldehyde or a ketone in your solution. Basically, it's a very definitive test for an aldehyde. Benedict's test, again, I just want to point out these chemical tests, you don't need to memorize them. You can put them in your notes, certainly. It's useful for your lab and for your homework, but I'm not going to test you on these on the exam. For Benedict's test, we use a Benedict's reagent, which contains the copper 2 ion. And these in particular will react with aldehydes that have a hydroxyl group right next to it. So this is, for example, 2-hydroxypropanal. So it's a propanal aldehyde with a hydroxy group right next to it on the second carbon. What happens is basically when you add this in, it will oxidize the aldehyde to the carboxylic acid. And what you're left over with is a brick red solid. So you take a copper 2 sulfate solution, which is nice and blue. You treat it with one of these 2-hydroxy aldehydes, and you end up seeing a brick red solid that forms. So, oh yeah, here, great. We have the picture here to show you. Now, the way that this is mostly used is for sugars. Again, that's in the next chapter. And these saccharides, basically, if they have an aldehyde next to a hydroxyl group, which is pretty common in a lot of sugars, you'll see a positive tolerance test, which looks like this, copper 2 sulfate. And this is with a positive test. This is the copper 1 oxide that forms. Okay, next up, talking about reduction. So for aldehydes and ketones, just as the way that the alcohols can be reduced, or I'm sorry, alcohols can be oxidized to aldehydes for primary alcohols or ketones for secondary alcohols, the reverse reaction can occur as well. If you treat an aldehyde with a reduction reagent, for example, sodium borohydride, this isn't a compound that you had to learn about before, but it's NaBH4. So it's the sodium ion and the borohydride ion, which is BH4 minus. Or if you just treat it with hydrogen gas, for example, what's going to happen is the carbon-oxygen double bond is going to be broken, and you'll turn that carbonyl into an alcohol. Oh yeah, you need a catalyst. Sorry, you do need a catalyst like nickel, platinum, or palladium to add a hydrogen to the carbonyl group. So here, if we take, for example, propanal plus over a catalyst that's platinum, for example, what happens is what was our aldehyde here is going to be reduced now from 2 bonds to an oxygen to 1 bond to an oxygen, and the other bonds are going to be filled up with hydrogen. So this carbon gets a hydrogen and the oxygen gets a hydrogen as well. Oh, these are going to be on the test, by the way. Yeah. The tolerance test and Benedict's test, not on the test. This stuff is now, this material is back on the test. Now, for example, for an aldehyde, we know we turned it into a primary alcohol. For a ketone, it's going to be turned into a secondary alcohol. And we do the same thing here where we took acetone, we add hydrogen over a nickel catalyst that breaks the carbon-oxygen double bond, gives you the carbon-oxygen single bond, and the 2 bonds that are left over now, we have new carbon-hydrogen and oxygen-hydrogen bond. Okay, let's go ahead and give it a shot. For sample exercise number 7, select the product that's correct for the oxidation of this alcohol. So look at the alcohol, look what's going to happen as it gets oxidized, and come up with what the answer should look like. So go ahead, pause the video. When you come back, we'll take a look at the answer. Okay, so let's take a look. We have a secondary alcohol here, right? So we know that secondary alcohols will be oxidized to ketones. And it looks to me like the alcohol is on the second carbon. So only ketone that I see here is actually B. And sure enough, that ketone is on the second carbon. So it looks like it's good to go. There we go. Okay, now how about this? We have now propanol, and we're going to do sequential oxidations. And give me the reaction for both when we oxidize it the first time. What's the product when you oxidize it the first time? And what's the product when you oxidize it the second time? Go ahead, pause the video here. And when you come back, we'll take a look at the answers. So pause. Okay, so we have 2 sequential oxidations because this is a primary alcohol. The hydroxyl group's bonded to a carbon that's only bonded to 1 other carbon. So primary alcohols are first oxidized aldehydes. So the only aldehyde I see is here, number 3. So the first one should give us 3. Now, aldehydes can be oxidized again into carboxylic acids. So the correct sequence should be this goes into 3 and that goes into 4. So yeah, P is 3, C is 4. Okay, so now let's go ahead and write the products for 2-propanol. Tell me what's going to happen when it undergoes oxidation, what's the product going to be, and what's going to be the product when it undergoes dehydration, and show me those reactions. So pause the video here, work this out, and then we'll take a look at the answer when we come back. So pause. Okay, so let's take a look. So first with oxidation, 2-propanol, first off, is a propane that has an hydroxyl group on the second carbon. So it looks like that, isopropyl alcohol. When it undergoes oxidation, what happens is you take your secondary alcohol group here, that's going to become a ketone. So we lose the hydrogen and the hydrogen here. That gives us a carbon double bonded to an oxygen, and we end up with a ketone, acetone in this case. Now, dehydration, on the other hand, that's where we're going to take the hydroxyl group, we're going to lose the hydroxyl group and lose a hydrogen from a neighboring carbon and form alkene. So we form a double bond. Now, you can form a double bond this way as well. There's no difference between those two, so don't worry about that. Okay, all right, well, that covers us now for chapter 12. So let me know in the comments below if you have any questions. I'll talk to you very soon. Until then, bye-bye.